Hello and welcome to Saturday's edition of Cracking the Cryptic, and today we're going to do a puzzle by Willy Wonka. Now, we've featured Willy Wonka a few times over the last few weeks, and I have to say I really love his puzzles. They have become an absolute joy. He's certainly one of the best setters setting puzzles currently in the world, in my opinion. And I don't say that lightly. And the best compliment I can pay him is that every puzzle of his I've done has been, it's just given me a lot of pleasure. This one has a very interesting additional rule to normal killer Sudoku rules, so we'll check that out in just a moment. A couple of things to mention first. I was delighted to see how many of you enjoyed the Litz puzzle that I featured on the channel in yesterday's video. So it does seem to have been a very popular puzzle type, and I fully intend to revisit it therefore in the next week or so. So if I get some good Litz suggestions, we should do another video on that. I think it certainly seemed popular. Just a reminder for those of you who are patrons of the channel as well on Patreon, obviously thank you for supporting us there. And we have put up, or I've put up, my Solve for Fistimafel's 12x12 Star Battle, which is a fascinating Star Battle puzzle. In that there are sort of two ways to solve it. There's a sort of using standard Star Battle techniques way in which isn't easy, but it is doable. And then there's the way that Fistimafel intended the puzzle to be solved, which is mind-blowing. And we have a look at both variants in that video. So yeah, do check that out if you're a patron of the channel. It's over on Patreon right now. Now let me read you the rules for Willy Wonka's puzzle. We have got normal Sudoku rules apply today. In cages, digits sum to the small clue in the top left-hand corner of a cage. Let's pick a cage, this cage here. That means those three cells have to sum up to 20 without repeating a digit. Now, here's the kicker. Okay, one of the digits is worth twice its normal value in every killer cage in the grid. This digit is to be determined. Right. So that's what's going to make this puzzle a bit different. As I say, can't recommend it highly enough. Do have a go yourselves. The way to play is to click the link under the video. If you want a guide on how difficult this puzzle is, it's 4 stars out of 5 for difficulty on Logic Masters Germany, and of course a 95% approval rating, or it might be 96%, but it's very approved of. So do have a go yourselves. With that, I get to play. Let's get cracking. Now, so ordinarily there are a few cages in this puzzle where I could immediately write in the options, but because I don't know which of the digits has a double value, just trying to think about this. So is there some way, or is there some way of noting obviously what digit is the double valued digit? I don't think there is. I mean, if there was a 36 cage or something in a limited number of cells, we might be able to do something, but there isn't. So probably, let me just stare at this for a second. Probably I'm going to start here. Why? I could start here actually. Both of these places look interesting. This one may be a little bit more interesting because these numbers all seem big. So ordinarily, I say it in every video, just about every killer Sudoku video, I trot out the line about, well, we know that this box here contains the digits 1 to 9, therefore we know it adds up to 45. Here, we know it does contain the digits 1 to 9, but we know it absolutely does not add up to 45. Because one of the digits is doubled. Anyway, let's get back and see if we can tell a bit more about which digit is doubled. We've got 20, 33... 49, 53, 73, 85. 85 is an enormous total. So, yeah, okay, so we can rule out some small digits from being the digit that gets doubled here, because I guess one way to think about it is if 1 is the special digit that's doubled, what would the total of the yellow squares be? Well, it would have to be 46 because the 1 would count for 2. It would be double its normal value, and the rest of the cells would be the same. But if these added up to 46, and I know all these cells add to 85, then these squares here would have to be very large indeed. They'd have to add up to 39, which is absolutely impossible. So 1 can be ruled out. I'm guessing 2 can be as well. 47. These then have to add up still to 38. It's nowhere near. I will just check 3 just for the sake of good order, but it's not going to work. So 3 means these sum to 48. These sum to 37. Doesn't work. 4. These sum to 49. So these sum to 36. Now, if we did put a 4 in these yellow squares, we could get closer, couldn't we? But not we can't get high enough, but we do get closer, because if we did put 4 here, for example, this would count for 8 because it doubled. Then we could put 7, 8, 9 in there, and they would add to 24. So we can get to 32. We need to get to 36, I think I said, but we're closing that gap. So let's try 5. If we go 5, this would add up to 50. These would add up to 35. Now, if we put a 5 in here, that would add up to 10. This would be worth 10. It doesn't quite work, because again, 7, 8, 9 would only be 25. 7, 8, 9 would be 24. We would need 25. So 5 doesn't work. But 6 will work. 6, 7, 8, and 9 are the options then for our special digit. Now, 6, 7, 8, and 9. So maybe I look at this box now. So this box adds up to, we've got 30, 46, 59. And my special digit is either 6, 7, 8 or 9. So this box either adds up to 51, 52, 53 or 54. So this domino either adds up to 8, 7, 6 or 5. All of which are possible. But I suppose one thing is that is a natural domino. That does not contain a special digit. Which we know anyway, because do we know for sure the special digit has to repeat here? I'm not sure I do, actually. If 9 was the special digit, this would add to 54. These would add to 31. And you can't make 31 in 4 cells without trickery. So Willy Wonka's trickery tells us that even if 9 is the special digit, it has to repeat. It appears not only here, but also down here as well. Which reconfirms the fact that you're not going to get 2 special digits in a box. So there is no... Look at this. 8 minutes into the video, I've not entered a single pencil mark yet. Let's see if we can rectify that sometime soon. So this is natural, but I don't know its total. Very beautiful. Very clever indeed. Look. I shouldn't be looking at the totals for all these cells. All I need to look at is the shape of these cages. All of these cages are either 2 or 3 cells large. So if my special digit is 7, for example, and I try and put it there, that's worth 14. I can't put 2 1s there. That does not work. So 7, 8, and 9 are absolutely impossible. You cannot put them anywhere in here. If you put the 7 there, obviously that just breaks immediately. It breaks the 13 cage straight away. So the special digit is 6. And I get a pencil mark because I know there's a 6 in there, therefore. So let me just think about this. So this adds to 51. i.e. 45 plus the 6 again, because we have to count the 6 twice. This, therefore, adds to 34. But the 6 counts twice. So the other 3 cells in here add to 22, and we can't use 6 again, so it must be 5, 8, and 9. So these cells are actually determined now. This can't be a 6 because that's in a 12 cage, and that would just be 12 on its own, and we can't put 0 in there. I'm not on the new software today. I should be. For some reason I'm not using it, so I can't show you that I could write 0 in there even though I don't want to. Now so 5, 6, 7, 8, 9. This adds to 51, which means these are... Oh, okay, these add to 8, but they can't, because that's 59 minus 51. Now, if we're making 8 and we can't use 6 or 5 in the total, this is 1, 7. These are 2, 3, 4, therefore, to complete the box. Still no digits in the grid. Okay. Oh, in fact, I do get a digit. This gives me a digit. Oh, this is gorgeous. Ordinarily, I was about to write in the pencil marks for this square, and I saw 7 there, and I was going to write 6 as a pencil mark. But of course, that a 6 cannot just be worth 6 in this puzzle. It's always worth 12. So in fact, 7 is impossible in this square. This square is a 1, and this is a 6. So this is a 7. These two squares sum to 8, but can't use 7 or 6, so these two squares are 3 and 5. 5 must be in one of those cells by a bit of Sudoku trickery. Look, we've locked 5s into rows 7 and 8 in 2 different boxes of the grid. So in box 9 over here, we know the 5 can't. We can't have a third 5 in row 7 and row 8. There must be exactly 2 5s in row 7 and 8, and we know roughly where they go. So the 5 in box 9 is going to have to be in row 9. Ah, okay. Here we go. Can 9 go in the 16 cage? The answer's no, because the other 2 cells would have to add up to 7, and they can't, because 1, 6, 2, 5 and 3, 4 are not available. So the 9 goes in the 15 cage, and the other 2 cells sum to 6 without using 5. So this is 2, 4, 9. This is 1, 7, 8. That's not 7, you can see. So this means a few things, I think. We can write 8 in as a pencil mark down here for exactly the same reason we wrote 5s in. But the thing that the digits that are interesting me are actually 2s and 4s, because that means that we've got to put 2s and 4s into 2 of these 3 squares, and this is a 24 cage. Right, okay, well we know for sure, therefore, that these 2 squares can't be a 2-4 pair, because there's no way, even with our special digit, we can make this square equal 18. So this square must be a 2 or a 4. Now, one of the digits 2 and 4 must appear in the 24 cage. Ah, okay, and it can't be the 2. And the reason it can't be 2 is if I'm trying to make 2 cells add to 22, even using the 6, the other cell would have to be a 10, which is impossible. So this must be 2. There must be a 4 in this cage. We now know that 2 of the cells have to sum to 20, which means we still have to use our special digit. So there's a 6 in here. 12, 6 and an 8. So this is a 4, 6, 8 triple. Oh, but there's an 8 down here, isn't there? Yeah, there is, from the alignments of the 8s in rows 7 and 8. So there's no 8 in there, which means this square must be an 8. Now, that's not 8, therefore. 1, 7, 8. 2, 4, 6, 8. Sorry about this. I'm now struggling again, as usual. 6 must go there, just by a bit of Sudoku, look. So we can remove 6 from those squares. 5, 8, 9 here means this is a 3 and this is a 5. In fact, that shifts the 8 down there, look. And we get another flurry of digits into the grid. Now, can we keep our flurry going? No. No, I can't. Bobbins. It's no use. I'm not actually sure where I should look now. Maybe this box again? This square's got to be the counterpart of this square. So this has got to be 3, 4, or 7. It can't be 7 anymore because of this 7. Okay, so this... yeah. Here we go. This domino sits beneath a 13 cage. I was about... Ooh, I almost made a mistake then. Because I was about to say... well, it wasn't a mistake, but I was forgetting the option that this could contain a 6 and a 1, but it can't actually, so that's okay. So the question is, this is a natural 13. It doesn't contain a special digit. So can we put 4 and 8 into this 12 cage? Well, the answer is no, because then there would be no way of making this domino add to 13, because 4, 9 and 5, 8 would have gone. And 5 and 6, 7 is just not available as an option. So this has to be 3, 9. And this has to be 5, 8. And now we've still got to put 6 here. We've got to put the special digit therefore is over on this side and can't go. It can't go in here. Because if it goes in here, this square would have to be a low digit because the 6 would already count for 12. So this is 6. These two squares, 12. These have got to add up to 8 without using 2, 6 or 3, 5. So this is a 1, 7 pair. 2, 4, 9 here. 2 comes over on this side. 4. It's a bit like it was down there. This has got to be 2, 4, 6. And presumably then, yeah, again, we can't have a 2 and a 4 in here. So we know there's a 6 in here. But this time the 2 could go in here because 2 plus 12 is 14. That would place an 8 in here. 4 plus 12 is... Oh, 4 plus 12 doesn't work because that would put another 6 in here and you can't have a 6 in there. A, because that's a 6, and B, because 6 does not equal 6 in this puzzle. It equals 12. So this is an 8. There is no 4 in here, and this square is a 4. And now what can we do? 2, 6, 8. 8 must be in one of those squares. Let's do a bit of Sudoku, see if we can tidy anything up. Ooh, that's interesting. The 23 cage would ordinarily have to contain an 8, because it would have to be 6, 8, 9. But here it can't contain an 8 by Sudoku, which means it must contain a special digit, and that special digit is a 6, so there was a 6 in this after all, but not a normal 6. So the other two squares add to 11, which we can't resolve. Okay. So maybe, can I do something? Yes, I can. Yeah. Look, if this is worth 12, these two have to be worth 12, so this can't be a 9. In fact, it can't be a 2, so this has got to be 4, 8. This is 2, 9, therefore, which means that adds up to 11. This is 5. That is working. The 2 fixes the 2 down here. That fixes the 2 here. 4, 9 here comes back over here, and we get some more digits. These squares have got to be 1, 3, and 9 by Sudoku. Let's delete the pencil marks there and replace them with 5, 7, and 8. We don't know much about those digits because there are no cages down here. That's not 8. Okay, it's actually quite symmetrical there, isn't it? We've also got no cages up here. So we can fill in the options, but I don't think this is likely to be where we have to look for the next breakthrough in terms of solving. That can't be an 8, just as this couldn't be an 8. Right. Be useful to get this 5. That must be a natural 5 because the special digit could never be in there. Hang on. 6s, look. Oh, yeah, this is nice. So, I don't know whether it'll give us any digits, but we can use the logic that we've been using a little earlier in the puzzle. 6s in rows 1 and 2 are locked into boxes 1 and 3. So where does the 6 go in row 3 of the grid? It's going to have to be in one of those 2 cells. Similarly here, 6 is locked into columns 8 and 9 in boxes 3 and 9. So we can ask where the 6 goes in column 7. It's going to have to be there. I don't know, this logic feels symmetrical, doesn't it? I'm not sure whether there's symmetry going on here that I'm not appreciating. Perhaps. 6, 11. Okay, now this 22 cage is interesting because it can't contain a 6. The 6 up here rules a 6 out of this domino. The 6 in this domino rules a 6 out of here. So we know that the 22 is a natural 22. It therefore contains a 9. But we can go further than that. But as we know it doesn't contain a 6, because 6 is worth 12 in the puzzle, it must be a 5, 8, 9 version of the 22 cage. That square means this is not 8. 8 is in this domino. That gives us an 8 in row 1, column 1. For which we should be very grateful, and there the trail runs cold, does it? No, we get another 8 there by Sudoku, which means we get an 8 here. Again, the logic is just feeling a bit symmetrical. I don't know whether that is true. Now, can we... Well, I'm going to try something here because these cages are all enormous. So is that 23 or 22? 23. Okay, so 23 plus 22 is already 45, plus another 20 is 65. Okay, so we can do some logic here. Let's highlight this and think about it. So if the purple squares add up to 65... But we know that this box adds to 40. We don't know it adds to 45. It doesn't. It adds to 51. Almost made a mistake. Oh, well, we can still do the logic I was intending. It just might not be as powerful. Okay, if we know this box adds to 51, and we know that this purple adds to 65, how do we convert that 65 into 51? Well, you can see we'd have to deduct those 2 cells and add in, let's colour those in, and add in those 2 cells. So that is how we would do the conversion. So we've got 65 minus blue plus green equals 45, which we could not 45, 51. I keep making a mistake. So that means that 14 minus blue plus green equals 0. which is quite cool because that tells you that blue is equal to 14 plus green, which means, and we can't put 6s into those, so this is incredibly constrained. Incredibly constrained. In fact, I think I've worked this out. If this was 1 and 2, which would be the minimum we could make these two cells would have to add up to 17, which would mean they would have to be 8 and 9, and we can't put 8 in either of them. So this simply cannot be 1 and 2, but the only other option where we can make these digits work, therefore, is 1 and 3, and we have to make them both equal to 9. And that must be useful, surely. No? What? Oh no, that 9 does give me something down here anyway. I was about to get perplexed as to how that wasn't helpful. 9, 9. Where does 9... In fact, yeah, if this is 9, this has to be 5. But better than that, where does 9 now go in this top box? By Sudoku, it can't go in those cells. It can't repeat in a cage, so it can't go here. So it has to go in the central cell. And now we know there's a 12 and a 9 in here, so the other cell must be a 2. So we get a 2-6 pair, which marries up, look, with a 2-6 pair over on the left-hand side. So there must now be a 2 in one of those two cells by Sudoku. These two squares have got to be 4 and 7. That can't be a 9, which means this is the only place for a 9 in row 8. So similarly, we get the 9 over there, of course. I feel like this is right on the verge of cracking now. I've got a 1-3 pair here. Still don't know the parity of this 5. Got quite a lot of digits in column 7 as well. 1, 3. In fact, yeah, because 6 has to be there. So this square can only be 1, 3, or 5. And that's part of a 16 cage. This is brilliant. So, is it possible this 16 cage does not contain a 6? Well, let's think about it. Let's try and put 5 into... We can see if this is 1 and 3. That would add to 4. This would have to be a 6 because 6 counts double. If this is 5 and this was 1, this square would have to equal 10. That's impossible even in this puzzle. If this is 5 and this is 3, this would have to be 8, which is impossible. So this is simply not 5. This is a 1-3 pair, which makes this square a 6. The 6... Oh, now the 6 can't go in the 9 cage because the 6 doesn't equal 6, it equals 12. So the 6 goes there, which means that's a 6, I think. That means this is a 5 by Sudoku. Still don't know what this cage is. Okay, have we exhausted everything now? This 5 gives us a 5, 7 at the bottom. So the 7 is now forced in box 6 because it can't go in the 5 cage even in a strange puzzle like this. 7 does not equal a number lower than 5. So the 7 goes here. Oh, this is a naked single. Look at that. 1, 2 and 9 have not been placed in the row. And there's a 9-2 pair in the column. That's got to be a 1, 1, 7. 1 has to live in one of those two squares. These 3 squares have got to be 3, 3, 5 and 8. That can't be an 8. Beautiful, beautiful. Look, the 3. Where does the 3 go in this box? It can't go in the 9 cage because it would need to accompany a 6, which is not a 6. There's no such thing as a 6 for the purposes of these cages in this puzzle. In fact, that would be quite a good way to think about it when you're solving, is just to say 6 is an impossible number. So 3 must go into one of those 2 cells, which is rather good because it means that square's a 5. Therefore, that's a 5, that's a 3. Now, is that useful? Maybe. 2, 6 pair now, so this square's got to be a 1, 4 or a 7. It can't be a 1 because there's a 1 in the column. So this is a 4 or a 7. This 5 is important, look, because now 5s are forced into the 9 cage where they must join a 4. 4s are natural. Where does 4 go in these 2 cells? This 4 tells us it must be at the top. That gives us all of those digits, all of these digits. Now this little 1, finally, not only does it give us 1s and 7s over there, but it tells me this 5 cage is a 2-3 variation on the theme. The 2-3 here does all sorts of things. 8, 3, 9, 2. That square should be a 9, I think. These squares here should be 2 and 7, which we can do. 8 here means 8, 5 gets resolved. 5, 4 gets resolved. We've got to put a 4 somewhere in box 6. This 4 fixes the 4, 6 here. Fixes the 6, 2, the 2, 3, the 3, 1. It's just gorgeous. Now, let's just make sure that we're not going to have a ricket at the end. This 4 gives me a 7, 7, 4, and that should be a 3. That looks good. Let's check. What does that say? Yes, looks good to me. So, there you go. What a brilliant puzzle again from Willy Wonka. I have to say, I do look out for this guy's puzzles now because they are such a pleasure to solve. I hope you guys enjoyed it. Do let me know in the comments. I do read them, and Mark will be back later, of course, with another edition of Cracking the Cryptic.